So good morning. I'm Georgios Karystinos from the Technical University of Crete, and this is the title of our project is Secure Communication based on robust 3D localization. A few words about the project. Our project was funded under Open Call 3. It started in October 2021. It was a short-term project, but due to COVID enforced problems and restrictions, we had to extend it. So it lasted for 8 months. It ended in last May. The partners are the Technical University of Crete, represented by me. I'm the Dean of School of Electrical and Computer Engineering at TUC, and Florida Atlantic University, represented by Professor Pados, who is the Director of Center for Connected Autonomy and Artificial Intelligence. The work of the US partner was funded by an NSF supplemental grant for experimentation on powder. The two teams are, as you can see on the screen, in the EU team, we had 2 graduate students and me, 1 PhD student, 1 master student and me. And in the US team, we had 2 professors and 3 students, 1 undergraduate and 2 graduate students. In our experiment, the objective of our project was to implement and experiment with data for secure communications and wireless platforms. And we specifically used the Argos measured data from the Argos V2 datasets. The Argos V2, it's version 2 datasets are channel traces, communication channel traces that have been recorded at the frequencies of UHF 2.4 gigahertz and 5 gigahertz bands. For diverse environments, they have cases with static environments, mobile users, etc., indoor, outdoor. And the base station, the Argos base station has 104 ports. So it's a 104 multi-antenna array. These are 2 photos of the Argos V2 base station. Okay, thank you. Oops. Okay, and these photos here show the mobile units that were used in the experiment in different setups. All mobile units had 1 or 2 antennas. For our experiments, we used units with 1 antenna. This is an example of the setup that we used that was used for the measurement of the data. This is Lopet Hall at Rice University, and you can see here the base station, and here probably you can see the 8 terminals. This is the static environment, and here is a map of this situation. So you can see the base station here, and placed here the 8 mobile, then the 8 mobile terminals. In this case, they are static. The objective for this experiment was the following: we want to transmit from the base station to a selected user, for example, user 1 here, and the signal that we transmit goes through is received by all other ones. So we want somehow to transmit secret information to 1 so that it cannot be received or decoded actually by the other users. And this way, with using only physical layer security techniques. And this brings us to the next slide. The core of the project was to establish secure wireless transmissions with frontline security. So we didn't use any key exchange protocols. We used spatial security, employing the multi-antenna base station that makes the signal inaccessible to our users through beamforming. And after we established spatial security, we built code-induced protection based on polar codes. This is something that has been investigated since the last 50 years. And the first solutions that achieve capacity were invented about 10 years ago with polar codes. So there's a big amount of work on this, and we implemented this work. And eventually we identified a few interesting things. One important aspect of the project that took us a lot of time and thanks to the 8-month extension of the project, we made it, was the calibration of the Argos data. The Argos data have been, our measurements provided by Powder, but for a few months, we couldn't interpret some strange behavior of the data. Eventually, we identified that the data needs to be calibrated because the measurements are not synchronized in frequency, time, etc. And this was very important. Otherwise, all results would be wrong. And actually, it is important because it is also used today. Today, there is our US the US team is working using this calibration techniques we implemented. So a few words about beamforming that we used. This is an image of the Argos V2, for example, multi-apply antenna array. Beamforming managed to direct the signal to a specific direction by techniques at the transmitter. And this way, you can see here that when if this is the legitimate user and this is an eavesdropper, when the signal is directed to the legitimate user, the SNR, the signal strength of the strength of the signal that the legitimate user receives is much higher than eavesdropper. And this is something that we employ to transmit secure signals. How? This is the base station again, the legitimate user, and this is the channel between the two nodes. Assume that the base station sends 8 bits. They are received by a legitimate user, not all of them correctly, because there is noise in the channel. So let's say the green ones are the ones that are decoded correctly, and the red ones are not decoded. At the same time, there is a second receiver. The same signal is transmitted to the second receiver. Since the channel, based on beamforming, is weaker, the second channel, the second receiver will manage to decode the last 2 bits. So this difference here, the 2 bits that are green and red here, are bits that can be decoded by the first and not by the second. And here we can hide our secret data. That's the basic principle of physical layer security. To achieve this, to attain this situation, we have to use smart encoding techniques here and decoding at the receivers, of course. And these techniques are based on polar codes. Now, the results of our experiment are the following. This is the setup that I showed before. At the first round, we have here, you can see some arrows. The 8 users transmit data to the base station. This has been done already in the data set. We got this data. We did data calibration. That is, we corrected the Doppler phase, the time shifts. These are figures before the correction and after the correction. The phase shifts, again, before and after. And the sampling time offset, this graph took us about a month to identify what the problem is and correct it. After the data calibration, we used beamforming to transmit towards the 8 users. The green arrow here shows that we want to transmit secret information to user 1. All others receive the signal, the same signal, are eavesdroppers. And we have many results, but I will show only one. We managed in this situation to achieve, when the SNR, transmitted SNR is about 15 dB to 20, to transmit secret information that is about 12 megabps. You can see that when the signal to noise ratio is very small, we cannot transmit secret information because both channels are bad. And the same happens apparently when the SNR is very large, because both the legitimate receiver and the eavesdropper have perfect channels. So you cannot hide anything. We do not have this situation with red and green bits. But in the intermediate case, we can tune the SNR to maximize the secrecy ratio. So this is something that looks like an optimization problem. We don't want to transmit with high max power, not with minimum power. There is an optimal power that maximizes secret transmission. This is the last slide. The highlights are the following. Through the project, we had the technical exchange, and we thank both institutions, both NSF and the EU for this initiative. We used a lot the data from the Powder platform, but actually we still continue working on it. We organized the workshop on in the end of the project, May 2022, in Florida Atlantic University. The workshop was on coding, data processing, time, space, series analysis, and security. And as I mentioned, we did data calibration on power data sets that it is not obvious to identify and also to solve. Next steps, we are going to get accomplishments beyond and after this NGIatlantic.eu collaboration. We are working right now on a journal paper that has some results, innovative results, theoretical results from our research, not directly connected to the experiment, but to polar codes. We are going to investigate secrecy coding for OFDM-based adaptive subcarrier allocation. There are many cases here to investigate. Our plan is to integrate hybrid ARQ for frontline security enhancement. And the most important, we had two students from Florida Atlantic University last month visited Utah. They were trained on Powder through an NSF fund grant. And we are collaborating on working for real time, because what I presented was with static data, recorded data. We're collaborating on implementing what you saw on real time implementations, which is not straightforward, and actually would be happy to see if there's a continuation of this funding scheme to support this research. Thanks a lot. And I'm open to questions. I think I'm okay with time, right?
Thank you very much, Georgios. George, it's great to hear about the success. And I'd like to just highlight a little bit about the supplemental fund that you had. As Deep Mehdi mentioned yesterday, the Dear Colleague letter 21048 was a dedicated supplemental fund for U.S. grant and NSF grantees, but the one that George, you had in your project was the supplemental fund from the Program for Advanced Wireless Research, or PAWR, which we mentioned yesterday. And so I just want to sort of highlight the difference between these two. So the DCL 21048, which was the one specifically for grant holders that are involved in the Computer and Network Systems Core and Secure and Trustworthy Cyberspace programs of the NSF, their grant had to be within those two. But what was very interesting about the PAWR supplemental grant, which actually preceded the NSF DCL and is still ongoing. What's interesting about the PAWR supplement is it's available to any NSF grant holder, regardless of the program that they're involved in. Now, of course, it has to be a proposal submitted to the either Powder, Cosmos, or AirPaw, and it has to be in relation to wireless networking or wireless topics. But it's my understanding that a number of our projects took advantage of this one because perhaps it predated the Dear Colleague letter, or they didn't, their U.S. partner didn't specifically fall within those two programs, Computer and Network Systems Core or Secure and Trustworthy Cyberspace programs, which are huge programs. But so I'd just be interested, George, to hear about the process itself, or perhaps Florida Atlantic were the ones that went through it. But are you aware of how easy or how hard it was to apply to Powder for this grant?
I don't know. They had already got the PAWR project, okay, before we started. So, and this is the reason they didn't apply for the DC eventually. But I let them know, but
Yes.
Since they had already funding for it, for working on powder, they didn't follow this. I don't know how hard it is. I cannot answer.
Okay. I mean, it's my understanding it's quite easy. And, you know, we were fortunate in that in our project NGIatlantic, we had partner University of Utah from powder and also Rutgers University from Cosmos. So, you know, they were able to, I think, make things a bit smoother when needed. But it's my understanding that it was fairly easy to apply, and then there was a fairly quick turnaround time.
Provided they have already an NSF grant, right? So
Yes, but as I mentioned, what's interesting about the PAWR supplemental grant, which is different to the DCL, is it's my understanding that it can be any NSF grant in any program, as long as what you're proposing to Cosmos, powder, or AirPaw, as long as it's a project related to, you know, wireless research. You know, okay. But it did open up. I know there were a couple of the applicants in our webinars that their U.S. partner, unfortunately, was not in one of those two programs, but they were in another program, and we were able to put them over to the PAWR supplemental fund. So it was quite nice. It was complementary. Now, I think the funding is a little bit less. I think it's 50,000 instead of 100,000. But what's really nice about it is, as you mentioned, the powder or Cosmos or AirPaw, they will basically do training. They'll support, you know, the program that has received the supplemental fund. You know, that they'll help the projects get set up, implemented, and things like that.
Yeah, because they have to make sure that the platform is continuously used, right? So
yes.
Okay.
I mean, what they insisted, I think, was that, and sometimes it was difficult because of COVID-19, but they had insisted that they would prefer that the EU partner that was involved would go to the platform to help with the setup and things like that.
That was our plan as well, but we
yes, it became difficult. Yes, but okay. Thank you, George.
Thanks.